know this is not what lasers sound like. But isn't it funny how a sound like this immediately makes you think lasers?
Laser swords, yep. That's indeed where my mind went immediately. They are so iconic for a type of science fiction movie, which I'm a huge fan of. Not sure if you already knew that. Massive fan.
No, I don't. See, you learn something new every day.
Right?
Lasers are becoming even cooler thanks to new technology.
And thanks to engineers like our dear Bosch research colleague Peter Stritt.
Actually, I find it really fascinating to see how former science fiction topics and thoughts are becoming real now, and we have the possibilities to test some of these in our laser labs.
From know-how to wow. The Bosch Global Podcast.
One thing is for sure, this is probably going to be our coolest episode ever. And I mean, lasers are just inherently cool.
Absolutely. But also, they're hidden in some of the most boring things at the same time. But we wouldn't want to miss them.
What do we concretely mean here?
For example, without lasers, our beloved office printers wouldn't work. And in the not-so-distant past, we also relied on lasers to listen to music or watch movies. You remember?
Oh, gosh.
Yeah.
I remember vaguely things like CD players and DVDs.
Well, they are a rarity now, I admit. Back to technology that is a little more current. My phone also wouldn't unlock without lasers. It's literally shooting lasers at my face when it tries to recognize me.
Without lasers, no scanners at the grocery store checkout.
Is that a boring example? Is it?
If you're in the German supermarkets and the ladies are doing their doing, and you can't pack the groceries fast enough, then it's not boring.
So really, without lasers, so many things would be different. From medicine to construction to space applications, lasers are basically everywhere. But perhaps most importantly, without lasers, the internet wouldn't work as we know it. Fiber optics rely on lasers for super fast data transmission, as do satellites.
And might I add, many products we use would look different without lasers because they play an increasingly big role in production. In manufacturing, lasers have not reached peak coolness yet, though.
The coolness of the laser applications and the coolness of the laser systems is still increasing.
So let me remind you all, this is our Bosch engineer at Bosch Research, Peter Stritt.
And here I am developing production processes for the products of the future.
So in his lab, Peter and his co-workers try to figure out how lasers can make production more precise, more efficient, more flexible, or how they could even enable completely new ways of creating a product.
Okay, but can lasers do production already?
Yeah, let's start there.
I imagine some robots wielding laser beams to cut sheets of metal. What do you say?
So you've done that so dramatically, but you're already a few steps ahead, Melena. So I'm going to have to break you a little bit.
Fair? Please do so.
First, when the laser systems were developed, there was only low power systems available. So the power was sufficient to heat material, and so you had some sort of heat treatment with your laser systems of the material or metals.
So when done in a smart way, and when you also control the cooling of the metal accordingly, that results in the hardening of the metal.
So hardening was the first task that lasers did on factory floors.
Exactly.
And then with increasing power and better focusability of the laser system, it was possible to actually melt the material. And thereby cutting was established and also welding of material was established.
There they are, my industrial-grade laser cutters. But interesting to hear that at the same time you couldn't just cut, but also join pieces by laser welding them.
Mm-hmm.
And then the next step was to form the laser beam in time, to have something like pulse shaping or something, to pulse the laser system. And from that on, different technologies like drilling and structuring were developed.
So just to make everything clear, structuring means that you can remove material from the surface. It's an ablation process to create a certain structure.
That sounds a bit like laser engraving, doesn't it?
Yeah, I suppose you can say that. Yeah, so there are these things lasers can do: hardening, cutting, welding, structuring, and, as Peter mentioned, drilling.
What's really fascinating to me is, well, wait, actually, it's multiple things. Yeah.
I was about to say one.
One, I mean, this is light. How can you do all of that with light?
Mm-hmm.
I mean, I kind of get it. Extremely focused light creates heat when it gets absorbed.
Mm-hmm.
But then, number two, how can it do all these different things at once? What determines whether a laser drills a hole or transmits data to a satellite without, well, destroying it, or whether it creates a weld or hardens a material or, in medicine, corrects someone's vision? God, I really like my questions.
I like where your mind is going, and I do also appreciate the questions, but I'm pretty sure we have an expert who will be able to give you an answer.
Yes, actually, it's really fascinating that one little tiny laser spot can be shaped in such different ways that different processes can be achieved.
Et voilà, our Bosch engineer to the rescue.
Laser systems exist in different forms. So we have different wavelengths, for example, available, which possess then different physical properties in absorption, for example, on the materials. But the next thing is that lasers can also be shaped and focused in different ways. And that brings us to a very versatile tool, because you can either use the laser system as a huge heat source, or you can even focus it to a tiny spot and thereby achieve evaporation on your material.
So as you can see, on one hand, extremely versatile, but on the other hand, typically one laser system can only fulfill one of these functions.
Mm-hmm. Okay, got it. So my laser can either harden or cut or weld.
Or drill, but in essence, correct. You can't switch from one function to another. Instead, you need multiple laser systems if you want to perform different tasks. But now there's new technology entering our factories.
Beam shaping lasers.
Different franchise, but beam me up.
You have the choice of either having a cutting process or a welding process. And you can do both with one system just by switching the beam shape, for example.
And by beam shape, Peter means what the cross-section of the beam looks like. Because, of course, the center of a laser beam always propagates in the form of a straight line that never changes. But what the new technology can change is the intensity profile perpendicular to the propagation direction. So when you travel across the beam.
So if I'd hold a sheet of paper into the beam, in the simplest case, what I would see is a circle of light, or rather a disc, assuming that the laser beam is round like a rod.
So this is something I always love about a podcast, is we learn about cute ways of naming things. So what you've just described is what Peter calls a top hat shape. So if you would plot the intensity of the light on a graph, it would actually look like a top hat. So going from left to right, the intensity suddenly jumps up 1 point, then stays constantly high before suddenly dropping back down to 0.
That makes so much sense. Got it.
And now it's easy to imagine that you can smooth the edges a bit. And instead of these very steep cutoffs, you can have more slope-like shapes.
So basically like an elevation of a roller coaster. And at the top, or rather in the center of the beam, the intensity is at its peak. And on the other side, the energy level decreases again.
Peter calls this a Gaussian beam shape.
Today, 99% of the laser beams used for material processing have either a Gaussian or a top-hat beam distribution. And the newer system and laser optics technology enable the formation of different beam shapes now. And with that technology, today it is possible to create lines. You could think of triangles, multi-spots, rings, or other beam distribution. And it is even possible to form non-symmetric laser beam shapes, such as a C shape, which might be beneficial in certain non-symmetric laser applications.
That sounds so cool. So Peter definitely didn't lie when he said earlier that lasers are actually increasing in coolness. But aside from that, what are the benefits of a triangular shape or a C shape or the other shapes that beam-forming lasers can produce?
One of them is pretty easy to figure out. Peter said the new lasers can create multi-spot beams. And that simply means split one beam into multiple beams. So simply put, if you make 2 beams out of 1, you can increase productivity.
Right. So in the end, you make better use of the laser system.
Exactly. Now, what the new shapes, triangle, ring, C-shape, so on, you mentioned them, what they could be good for is Peter's job to explore. He uses these new types of lasers in his lab to conduct experiments and see what benefits they have and how to optimize them.
And with each experiment, we want to increase the understanding and the knowledge of this laser material interaction and build up some sort of model which we can then use for further optimization.
The problem is this becomes very complex very fast. Let's not even talk about all the different shapes that are now possible. Let's just assume that there are 3 knobs that you can turn to control how your laser and your workpiece interact in a machine.
I would think of the knobs for laser power, velocity, and also the laser beam size or the focal position on the workpiece.
Okay, that sounds actually manageable, I'd say.
If you now imagine that you not only have one single laser spot, but instead you would have some sort of array of laser spots. For example, if you would have 30 times 30 single laser spots or pixels, by that you would come up with 900 pixels, which again you would have to multiply with the number of parameters. And with that calculation, you can easily get in the range of having millions of possible parameter settings.
The parameter space explodes exponentially. So it really isn't possible to explore all the options.
Right. I mean, you can do millions of experiments.
Yes, you can. But, and that's what we do as well, you can enlist a little helper. And Melena, do you want to take a guess?
I don't know, enlighten me?
Artificial intelligence.
Oh, and I thought this couldn't get any cooler. But well, here we are. I want to know all about how Peter uses AI to solve this challenge of finding the optimal parameters for these new beam-shaping lasers. But shall we give him a little break, Shuko? Are you up for a little bit of fun? I know you are.
Fun is my middle name. Let's go.
I want to test your knowledge about lasers, and you can test mine.
Here we go. And listeners, I hope you guys are playing along as well from wherever you're listening to us.
Of course, we are playing Two Truths and a Lie.
Okay.
I will start, and I will give you 3 statements, one of which I have completely made up. Here are my statements. Is it either lasers can only produce red, green, or blue light? Or statement number 2, lasers can be used for cooling too? And number 3, laser is a German family name.
Oh, come on. That's so easy. Laser is definitely a German family name. No, jokes aside, I'm actually really hesitating between 1 and 2, but I think I'll go for lasers can only produce red, green, or blue light.
Oh, you're such an expert. Yeah, that's correct. That was my lie. There are yellow, orange, and purple lasers too. And in fact, dye lasers can produce any color in the rainbow. So you got it.
Yes, 1 point. Let's see what I can come up with. So here are 3 facts about lasers for you.
I'm listening.
Is it lasers can be used to roast meat? Mm-hmm. Lasers can be used to dry and iron clothes? Or is it lasers can be used to cut trees?
Roasting meat, drying and ironing clothes, cutting trees. I mean, wait, so we've been talking about... I mean, they're basically about heat lasers, right? So
exactly.
They should be able to roast meat. We've been also talking about cutting. So, I mean, cutting trees, I guess that should also be possible. Drying and ironing clothes. I mean, that would be fantastic, obviously. But I kind of have the feeling someone super smart from Bosch, of course, would have come up with some sort of tiny device which would make that possible. So I guess that's your lie.
Well done. So definitely that is my lie. Although there are some irons that have lasers in the name, just because it sounds fancy. But lasers really? Cannot be used to dry and iron clothes. So yeah.
So in the end, let's agree on the fact that we're both freakishly smart.
Although you know me, I'm competitive. I don't like a tie. But I'll accept this shared win. Coming back to the topic, it seems like the potential applications of lasers are infinite. And here's one of the wildest applications Peter has come across.
There is a new professor at the university in Stuttgart, and he did some calculations how laser drilling of tunnels would work in the future.
Wait. Did you say tunnels? Like road tunnels? That's incredible.
Yeah, well, it sounds incredible. We'll see if that actually becomes a thing. Because just like Peter's own work, there are still a few things that, they need to tweak and figure out.
Right. So he had the problem that the new beamforming technology unlocks so many options that he basically doesn't know where to start.
Yeah, but we just mentioned this a few sentences ago. AI to the rescue.
The optimizer might decide where to do the next experiments.
So the optimizer might say, hey, why don't you try these parameters? They look kind of promising. And of course, first Peter has to define what to optimize for.
There is the exploration mode where you would go into new unknown configurations and regions which you haven't tried out yet. And the other thing is that you could set up your optimizer in the exploitation mode, where the AI then tries to find best options in an already well-known region.
Okay, either try something new or improve on what you already know.
Yeah, and that way the AI can narrow it down. It can look at the results from previous experiments and all the parameters at the same time and help Peter decide what would be best to try next.
How can I picture these experiments, though? What are those laser processes that Peter develops? We listed them earlier: hardening, cutting, welding. Is it any of those?
The hope is that any laser process will eventually benefit from the new technology in one way or another. But of course, there are, again, some things that Peter is particularly interested in.
Here I am thinking in the direction of laser joining of highly reflective copper material, or what could be also done is the stabilization of so far really fluctuating and unstable processes like the welding process of die-cast aluminum, for example.
Those are all things that are hard to do with traditional lasers. Copper is so reflective, it doesn't absorb enough of the laser to heat itself up and melt. But perhaps a certain beam shape can make copper welding easier. That could be important for the manufacturing of electric drives, for example. His second use case, the welding of die-cast aluminum, that is useful for housing of control units, for instance.
What is the problem there with traditional lasers?
Die-cast aluminum laser welding seemed to be impossible for a pretty long time.
Welding die-cast aluminum can get a bit messy. There are splatters, so molten aluminum is thrown out of the weld.
A little bit like when you cook tomato sauce. Or even worse, when you put it in the microwave, uncovered. Pro tip, just don't. Seriously, guys. Don't do it, just don't.
It's not just a pro tip, it's a life tip.
You learn so much on this podcast, don't you, listeners? This is for Jeff, though, because he loves his microwave. Hi, Jeff.
He's going to love me saying aluminum. I don't know about tomato sauce, but for aluminum, Peter has already managed to reduce the spatter by using a modified Gaussian beam. When you look at the cross-section of the beam, there is an addition to a typical Gaussian beam intensity distribution, a donut-like ring surrounding it.
And the outer ring, actually, it can help to prevent the formation of spatters. So in that case, it can really lead to a quality increase.
When laser welding of die-cast aluminum becomes standard in manufacturing, that's a pretty big deal. Not the nicest sound, but super important to have this technology available.
I would really say that the development of such dynamic or formed laser beam enabled new product features or even new product designs by substituting other materials.
One feature of aluminum is, of course, that it's lightweight. So if it can be used in more products, that can make products lighter, leading to more benefits down the line.
And Peter doesn't stop there. Obviously, Bosch engineers don't stop there. He has more ideas how to use these new lasers to do things that were, hardly possible before.
If we have the possibility to join, for example, aluminum to copper, this would enable a whole new product design because we can actually have on the one hand side the aluminum part, which has the certain aluminum specific features like the lightweight and so on. And on the other hand, we have the copper part, which has the copper specific features like the good heat and electrical conductivity. And with having such a joining technology for both materials together, we enable new product design.
Joining metals as different as copper and aluminum becomes possible with these lasers because they're so adaptive. They can be shaped in a way that they produce just the right amount of heat in both aluminum and the copper part. A laser beam in a C shape, like Peter mentioned earlier, could be an interesting candidate here.
Okay, got it. It sounds like beamforming lasers have a bunch of advantages. Let me recap real quick. So they can make processes more productive because you can split one laser beam into multiple, and one laser can fulfill multiple functions. Correct?
And as we already mentioned before, those functions cutting, welding, structuring, ablating, or hardening.
And then they also produce better quality.
Less spattering, for example?
But I guess the biggest and most future-facing advantage is that they enable entirely new processes and combinations of materials.
I think we have proven lasers have not lost any of their coolness over the years.
Not at all. Quite the opposite. Thanks for telling us about it, Shuko.
You're very welcome, Melena, but I wouldn't have been able to do it without Peter Stritt. Everyone out there, thanks for listening.
If you think this podcast is as cool as lasers, leave us a review or tell all your friends about us. Bye, guys.
From know-how to wow. The Bosch Global Podcast.
This is Jeff's voice avatar. In the next deep dive with me, you will get more details about how Peter optimizes beam shaping lasers. He will tell us more about how he uses AI in order to get the results he wants even faster. Stay curious. The deep dive will be released on November 30th.